You push with the force of one finger, and out comes enough power to flip a car. Sounds impossible? It's not. It's physics. What if I told you there's a simple law discovered over 370 years ago that lets a tiny pump move a 5-ton excavator arm? One law, that's all it takes. It's called Pascal's law. And once you understand it, you'll see it hiding inside every machine around you, from your car brakes to airplane landing gear. Today, we're going to break it wide open. Welcome back to Hydraulics A to Z, the series where we go from absolute beginner to full understanding, one step at a time. I'm Jay. In episode 1, we covered what hydraulics is. Now, in episode 2, we go deeper. By the end of this video, you'll understand the exact science behind hydraulic force multiplication. You'll solve real problems, and you'll never look at a hydraulic machine the same way again. Now, before we get into the science, stick around until the end, because I'm going to show you something wild. We'll take a real hydraulic system, a JCB excavator, and calculate exactly how much force its arm produces. Actual numbers, actual areas, actual newtons. You'll be able to do this calculation yourself by the time we're done. But first, let's meet the man who made all of this possible. A French mathematician born in 1623 who changed engineering forever.
Blaise Pascal.
This wasn't your average kid. By the age of 12, he was figuring out geometry on his own, drawing shapes on the floor, proving theorems that grown mathematicians struggled with. By 16, he wrote a major paper on conic sections. By 19, he built one of the world's first mechanical calculators, the Pascaline, to help his father with tax calculations. The guy was basically an engineering prodigy. But the discovery that matters most to us? That came in 1647 and 1648. Pascal started experimenting with fluids and pressure. He filled tubes with mercury. He carried barometers up mountains. And what he found changed our understanding of how liquids behave under pressure, permanently. So here's what Pascal figured out. And honestly, it's beautifully simple. He said, when you apply pressure to a confined liquid, a liquid trapped in a sealed container, that pressure doesn't just stay where you pushed. It transmits equally in all directions throughout the entire liquid. Every square centimeter of that container feels the exact same pressure. Let me say that again, because this is the foundation of everything. You push on one spot, the entire liquid pushes back, everywhere, with the same pressure. Not less, not more, the same. That's Pascal's law. And here's where it gets exciting. Because this one idea is what makes force multiplication possible. Alright, now here's where the magic happens. Imagine you've got a U-shaped tube, sealed, filled with oil. On the left side, there's a small piston. Its area is just 1 square centimeter, tiny. On the right side, a much bigger piston, 100 square centimeters. Now, you press down on the small piston with a force of 10 newtons. That's about the weight of a 1 kilogram bag of sugar sitting on your hand. Not much, right? But here's what happens. That 10 Newton push creates pressure. Pressure equals force divided by area. So 10 divided by 1 gives us 10 newtons per square centimeter. Now Pascal's law kicks in. That 10 newtons per square centimeter travels through the oil. It reaches the big piston. And because the big piston has 100 square centimeters of area, the force on that side is 10 times 100. That's 1,000 newtons. You pushed 10. You got back 1,000. That's 100 times the force. From one simple law. Now wait. Before you think you've just discovered free energy, there's a catch. Physics always balances its books. You gained force, but you lost distance. That small piston? It has to move 100 centimeters down just to push the big piston up 1 centimeter. You multiply force by 100, but you divide distance by 100. The energy stays the same. Work in equals work out. No free lunch. But here's the thing. In most hydraulic machines, you don't need the big piston to move far. You need it to push hard. And that's exactly what this gives you. Let's lock in the math. Don't worry, it's simple, and you only need 3 things: pressure, force, and area. The core formula is pressure equals force divided by area. P equals F over A. If you know any 2 of these, you can always find the third. Need the force? Multiply pressure times area. F equals P times A. Need the area? Divide force by pressure. A equals F over P. That's it. 3 formulas. They're all the same equation, just rearranged. Now let me give you a trick to remember this. Picture a triangle. F sits on top. P and A sit on the bottom, side by side. Cover the one you want to find, and whatever's left tells you the formula. Cover F. You see P times A. Cover P. You see F over A. Cover A. You see F over P. Easy. Burn this triangle into your memory. Let's use this for real. You've got a hydraulic car jack in your garage. The small piston, the one connected to the pump handle you push, has an area of 2 square centimeters. That's about the size of your thumbnail. The big piston, the one that lifts the car, has an area of 200 square centimeters. Now you pump the handle and push with 50 newtons of force. That's a comfortable one-handed push. Question: what force lifts the car? Let's work it out. Step 1. Find the pressure. P equals F over A. That's 50 divided by 2. Pressure equals 25 newtons per square centimeter. Step 2. Find the output force. F equals P times A. That's 25 times 200. The answer? 5,000 newtons. That 5,000 newtons is enough to lift about 500 kilograms, half a ton, from one hand on a pump handle. That's Pascal's law doing the heavy lifting. Literally. Let's do another one. Something you use every single day, but probably never thought about. Your car's brake system. Here's how it works. You press the brake pedal with your foot. That pedal pushes a rod into something called the master cylinder. The master cylinder has a small piston with an area of 5 square centimeters. Your foot creates about 100 newtons of force on that piston. Now, hydraulic fluid carries that pressure through brake lines to all 4 wheels. At each wheel, there's a bigger piston inside the brake caliper. Let's say each caliper piston has an area of 50 square centimeters. So what's the force at each wheel? P equals 100 divided by 5. That's 20 newtons per square centimeter. F at each wheel equals 20 times 50. That's 1,000 newtons per wheel. 4 wheels? 4,000 newtons total braking force from 1 foot press. And that is how you stop 1,500 kilograms of car at 60 miles an hour. Pascal's law, keeping you alive every time you drive. Here's something that might surprise you. A Boeing 737, one of the most common planes in the sky, has 3 completely independent hydraulic systems. System A, System B, and a standby system. Why 3? Because if one fails, the other 2 keep working. If 2 fail, the standby still controls the critical flight surfaces. Hydraulic failure on a plane is so dangerous that engineers tripled the safety net. 3 separate pumps, 3 separate fluid reservoirs, 3 separate pipe networks, all running Pascal's law, keeping you safe at 35,000 feet. Remember at the start, I promised you a real excavator calculation. Here it is. A JCB excavator's hydraulic pump creates a system pressure of about 250 bar. Now, 1 bar is 100,000 pascals. So 250 bar is 25 million pascals. That's 25 million newtons of force per square meter. The hydraulic cylinder on the boom arm has a piston area of about 200 square centimeters. That's 0.02 square meters. So the force on that piston? F equals P times A. 25 million times 0.02. That's 500,000 newtons. 500,000 newtons from one hydraulic cylinder. That's enough to lift roughly 50 tons. And remember, this comes from a pump no bigger than a basketball. Small pump, massive force. Pascal's law at work on a construction site near you. Before we wrap up, let me save you from the 3 mistakes every beginner makes. Mistake 1. Forgetting to convert units. If your area is in square centimeters and your pressure is in pascals, which use square meters, your answer will be completely wrong. Always convert first. Mistake 2. Thinking you get more energy. You don't. Force goes up, distance goes down. Energy stays the same. Mistake 3. Assuming Pascal's law works with air. It doesn't. Not the same way. Air compresses. Oil doesn't. That's why hydraulics uses oil. Let's lock in what you've learned today. Takeaway 1. Pascal's law says pressure applied to a confined fluid is transmitted equally in all directions. That's the foundation. Takeaway 2. Force multiplication works because a small force on a small area creates pressure. And that same pressure acting on a larger area creates a much bigger force. Takeaway 3. You don't get free energy. Force multiplies. Distance divides. Energy is always conserved. Takeaway 4. The formula triangle, F on top, P and A on the bottom, is your best friend for every hydraulic calculation from here on. Memorize it. Use it. Own it. In the next episode, episode 3, we're getting inside the machine. We'll break down the 6 core components of every hydraulic system. The reservoir, the pump, the control valve, the actuator, the relief valve, and the filter. You'll see exactly how they connect, how oil flows through the circuit, and what happens when each one fails. If you thought Pascal's law was cool, wait until you see the full system in action. That's next time. If this video made hydraulics click for you, smash that like button. It tells YouTube to show this to more people who want to learn engineering. Subscribe and hit the bell so you don't miss episode 3. And drop me a comment. Tell me, which calculation surprised you the most? The car jack? The brakes? Or that excavator? I want to know. Thanks for watching. I'll see you in the next one.